This is Mr. Barrett. I'm going to be showing you the PowerPoint on gases. So for gases, they're unlike liquids and solids. Obviously, they expand to fill their containers. They're highly compressible. Think a lot of air shocks. And they have extremely low densities. Just think a balloon versus a water balloon. Now, what are the key characteristics we actually use to measure gases? One of the key characteristics is pressure. And pressure is the amount of force applied to an area. So it turns out that one atmospheric pressure is about a 1 meter squared column of air. And that's all the air on the planet going all the way out to outer space. Atmospheric pressure we want to think of as weight per area, because force is particularly in newtons, is a unit of weight. So what do we have for units of pressure? Pascal is 1 Newton per meter squared. We have bars, which are 100 kilopascals. And then, of course, we have millimeters mercury, or torr. This graphic that we're looking at right now shows a barometer, and it's showing the height of mercury, and the height that it reaches is based on the weight of the atmosphere over the area of this pool of mercury. So the units are literally the difference in height measured in millimeter of 2 connected columns of mercury. All right, so 1 atmosphere, again, our atmospheric air pressure, what we use for standard pressure is 1 atmosphere in 760 torr, 760 millimeters mercury. In this picture, we're looking at a manometer. From a manometer, we're looking at the pressure of an enclosed gas right here, and then we have some mercury that's in this U-tube. Because we see that the height is not even for the mercury within the U-tube, we know that there's a difference in pressure between the enclosed gas and the atmospheric pressure. Since the mercury is being pushed closer to this end of the tube, which I'm circling right now, we can tell that the gas is of higher pressure than the atmosphere. Thus, we would need the pressure of our enclosed gas would be the pressure of the atmosphere, because it's pushing against this column of mercury, plus the height, and the height we of course want to record in millimeters. So if we use our units in millimeters mercury, and if the substance is mercury, we can use that to calculate the pressure of the gas. Standard pressure, normal atmospheric pressure at sea level, is equal to all of these units, as I've discussed before. All right, Boyle's law. So there's a lot of different gas laws in terms of the description of what happens when you squeeze a gas, you cool a gas, you heat a gas. Any changes to a gas are described by gas laws. Boyle's law is the relationship between pressure and volume. And essentially what it means is that if you increase the pressure, you decrease the volume. And you can see this from the graphic here. Know that pressure and volume are inversely related. You do not technically need to memorize this relationship. So if I click on this, didn't quite work, but the graphic is supposed to show that as you increase the pressure, the volume decreases. All right. Pressure and volume are inversely proportional, as I said before, so we could plot it out and you would see this graph showing the inverse relationship. Charles' law is a direct relationship between volume and temperature. If you increase the volume, you increase the temperature. This plot, as you can see, represents a direct relationship. Now there's Avogadro's law. This is the relationship between the number of moles and the volume. And again, it's a direct relationship. And that makes sense because if you increase N, which is your number of moles, you'll increase the volume. And this makes sense in the respect of filling up a balloon. You keep pumping air into the balloon, you're increasing the moles in the balloon, you increase the volume of the balloon because the pressure is being kept the same on the inside and the outside. All right, one of the cool things about Avogadro's law is it allows us to do stoichiometry. So you can actually use volumes in your stoichiometry equations as long as the temperature and the pressure stay the same before and after. So you can literally take, if I know I have 2 liters of this, then I know I will produce 2 liters of this. Why? Because it's a 2-to-2 mole-to-mole ratio. I don't actually have to convert it using PV equals nRT into moles. I can actually just use the mole-to-mole ratio to do my conversions. And that's assuming that conditions are the same before and after the chemical change. Now, the ideal gas equation. This is our Pivner. So by combining Boyle's, Charles, and Avogadro's law, you get this relationship on the bottom. That relationship on the bottom allows us to have the ideal gas constant, and the constant is known as R. There are many different values for R, and they're all relatable to one another. So depending on which R you use determines which units you use in PV equals nRT. So if you use this top gas constant, which is 0.0821 for most of us, you would be using liters for your volume, atmospheres for your pressure, and moles, and then Kelvin for your temperature. If we were using this one down on the bottom, we would have to use torrs for our pressure instead of atmospheres when we actually plug in numbers into our equation. All right, so this is the derivation for how we actually get from the relationship between volume, moles, temperature, and pressure, adding in the gas constant, then we get that final equation. All right, moving on. Density of gases. If we divide both sides of the ideal gas equation by volume and by RT, we can get this form of the equation. We know that moles times molecular mass, otherwise known as molar mass to most of you, equals mass. So by multiplying both sides by the molecular mass m, it gives you this equation. It's really important. I'm going to go back here to understand how we got from here to here. And when we look at this equation, see how we have, this is just Pivnert rearranged. So we have moles over volume. And then if we change our moles and represent it by mass, we now have molar mass on this side. So it's a way of being able to include density in the gas equation. So mass divided by volume, of course, is our density, and it's equal to the pressure times the molar mass divided by the gas constant times the temperature. And again, you want to make sure all of your units work with one another. All right, this is the same thing I just said before. Moving on a little bit further. This is another derivation of it, where molar mass, we can actually use the density of a gas, the temperature of a gas, and the pressure of a gas to calculate its molar mass. That would be something like the molar mass lab, which we can do in this class and measure the molar mass of a gas. All right, Dalton's law of partial pressures. The total pressure of a mixture of gases equals the sum of the pressures that each would exert if it were present alone. So in other words, if I have my mixture of gases, pressure of gas 1, pressure of gas 2, and pressure of gas 3, and so forth, if I add up all of those pressures, I'll get the total pressure in that container. Moving on. So whenever you collect a gas over water, you always have to remember that water vapor is mixing in with that gas. So if I have this decomposition of this chemical right here, and it's producing a gas and it bubbles up into this gas collection beaker here, what we have to note is that the pressure, once it's set equal to the atmospheric pressure, the total pressure on the inside is a combination of the water vapor pressure plus the gas that was collected. To find the pressure of the desired gas, that means you have to actually subtract the vapor pressure of water from the total pressure that you have calculated here by setting it equal to the atmospheric pressure on the outside. The kinetic molecular theory plays a huge role in this entire unit. We have to know that the kinetic molecular theory basically means that molecules are constantly in motion. The more energy you give them, the faster they move. The main tenets of the kinetic molecular theory is that gases are large numbers of molecules and they're continuously in random motion. The combined volume of all the molecules in a gas is negligible relative to the volume in which the gas is contained. What that means is that, let's see here, that when you mix gases together for the molecules, your total volume, the differences when you mix them together are not that different. It's tough to explain it with just this graphic right here. Attractive and repulsive forces between the gas molecules are definitely negligible, and that's what we actually call an ideal gas. It's where we assume that there's no attraction or repulsion between the gas molecules. The other tenet of the kinetic molecular theory is that energy can be transferred between molecules through collisions, but the average kinetic energy of the molecules does not change with time, as long as the temperature of the gas remains constant. So we can actually use this definition for temperature. It's the average kinetic energy of molecules. It's essentially the average speed of the molecules within the container. The average kinetic energy of the molecules is proportional to their absolute temperature, as we talked about before. Now let's talk about another property of gases, fusion. Fusion is when gas molecules escape through a tiny hole into an evacuated space. So if I have a container here and I have a hole, fusion is the rate that they're escaping or moving through that hole. Diffusion is the spread of one substance through a space or throughout a second substance. It's when it essentially spreads out over a period of time. This video won't work, but I think most students in this class by this level understand what diffusion is. Moving on, let's move beyond Boltzmann. Let's move beyond that. Real gases we need to talk about. In the real world, the behavior of gases only conforms to the ideal gas equation at relatively high temperature and low pressure. If you increase pressure or decrease temperature, gases actually start sticking to one another, and that's when they start behaving real. So an ideal gas is when PV over RT is equal to 1 mole. And that only happens, again, when you're at high temperature and low pressure. When you flip those around, the gases behave a lot more real, and they start sticking to each other. All right, derivations from ideal behavior. These are some of the things that I talked about. The assumption made in the kinetic molecular theory breaks down at high pressure or low temperature. Moving on. Moving on. We don't need to talk about that, and that's it. If you have any other questions about gases, please let me know.